way more easily than it was before. But hello, I'm Jessica or Jessie. I'm a grad student at the University of Notre Dame working with Chris Houck and Nicholas Lenner. And I'm excited to be here today to talk to you guys about recreating LRIS slit masks for use with multi-slit observations. So I'm sure many of you here are aware of the fact that LRIS has been used for a wide range of science over the almost 30 years that it's been in use. Just a quick list of some of those. We're studying open cluster white dwarfs, getting stellar spectra, looking at high redshift galaxies, getting galaxy spectra, looking at Lyman alpha emitters, looking at the circumgalactic medium, which is why my group initially got interested in this project, trying to find new galaxy quasar pairs for doing absorption line studies. But there are many more things that LRIS has been a part of over the years, and there's a diverse archive that has been built up with multi-slit observations that's currently a bit difficult to use if you were not the original observer. And that's because the sky positions of the slits in the slit masks were not stored alongside the observations in the archive. So if you're somebody who wasn't affiliated with the original project and knew what went in with designing the slit mask and what the targets were, it's kind of hard for you to figure out what actually is in the observations that you're trying to look at in terms of what objects were observed, what the spectra correspond to. There are other spectrographs like Deimos and Mossfire that do include this information, but unfortunately LRES doesn't. However, mask designs were stored in a separate archive at UCO-LIC, and while that doesn't include the sky positions of the slits, it does give us the mask design information, which we can use to bridge that gap and calculate the sky positions, which is what my work involves. So the LRIS slit masks are created with the AutoSlit software. You get a design that looks like this, and a whole bunch of output files that incorporate all of the design information that you need to create the mask so that it can be used at the telescope. And this information is what was stored at UCO-LIC. And I've developed a code, Tilsa2a, to reproduce that missing sky slit position, taking either the input from the archival masks or the AutoSlit output files, and calculating the slit sky positions, and as part of that also producing a FITS file that allows for pipette integration if that's what you're using to do your data reduction. So I'll talk about that a little bit later. But the basic idea for the code is to transform those stored slit positions from the coordinate system that they are stored in, which is the coordinates that the mask milling machine uses when it's creating the masks. And going back to sky coordinates, we have to step through the coordinate system that's used for the mask itself. You can see that here in the little diagram representing the slit masks. And that's done by first inverting all of the calculations and steps that AutoSlit does, hence the name of the code, and then also performing a correction to bring that resulting astrometry into agreement with our modern Gaia frame. A little bit more detailed breakdown of all of those steps is there on the slide. The important takeaway here, all of this goes into inverting AutoSlit, and then we perform a correction to align the mask with current Gaia astrometry. The output files that you get after running are the FITS file that has all of the mask information, a region file that you can load into DS9 to check your slit positions, as well as a quick look plot that contains a plot of all the slit positions, as well as cutout images of the alignment boxes for the mask, so you can easily check right after you run the code, the alignment of the mask on the sky, and check that you're happy with it. This FITS file is what allows for the integration with pipette. So as long as you run Tilsa2a with the output from AutoSlit directly, you can't do it with the UCO-LIC files, unfortunately. But as long as you have that, you can append the FITS file output to your pipette trace files. And when you run pipette and get your extractions from that, you will have the ARIAN deck information alongside that like you would for other spectrographs. If you want to see the step-by-step breakdown of how all of that functions, the pipette documentation has a good explanation for how all of that works. And I have to extend a thank you to the pipette team and Sunil Simha especially for helping get all of this integrated on the pipette side of things, so that if you're using the software, you can now get your pipette reductions for LRES the way that you could for other spectrographs. So I've talked a little bit about how the code functions and what it does, and I'll talk a little bit about the performance of the code. So I'm going to start with why we have to perform that correction to modern astrometry in the first place. And that comes from the fact that when you invert all of the autoslit calculations, you're going to reproduce the input astrometry that was given to autoslit when the mask was created. That doesn't necessarily match up with modern astrometry. And you can see systematic offsets in the mask positions from where you would want them to be on the sky. And if you're trying to use this to be able to match with observations and know what lies in all of your science slits, you really want to be as accurate as possible. So TILSA-2 uses the alignment boxes and calculates the offset between the centers of those boxes and the objects that should lie in them to perform a linear shift and bring the mask into alignment with Gaia astrometry. So with the correction, we get much better agreement. This is one of the more drastic cases with the shift that was necessary. Some of the masks do not require shifts at all. The agreement between the astrometry that we produce with autoslit and the modern astrometry is already really good. So TILSA-2 decides to not apply the shift. But when we run the entirety of the set of archival masks that were created from about June of 2020 before, and look at what corrections were necessary, we needed corrections to a little over half, about 55% of the masks. And of those masks that we applied shifts to, the overwhelming majority of those masks needed shifts of about an arc second or less. So this is on the order of the width of your science slits or less. So not a drastic correction, but enough of a one that you're going to want to make sure that you actually correct for it. You can also see in this plot more recent masks require smaller shifts, which makes sense since the more modern astrometry that would have gone into those is probably going to already be in better agreement with the Gaia astrometry. This histogram here shows the improvement when we incorporate the shift. So this left side shows the uncorrected offsets between the box centers and the objects in the Gaia catalog. And then the right side shows the corrected offsets. So we see a dramatic improvement in our alignment with the masks on the sky. And our final slit positions have an RMS error relative to the Gaia astrometry of about 0.1 arc seconds. So this is a good agreement with Gaia and is going to allow you to take those recalculated slit positions, go to the LRES archive if there is a science question that you're interested in where you think that you might have archival observations that would cover something that would be useful to you, and you can go and now match the slit positions with the archival observations to figure out which spectra you need to look at. I will throw up my summary slide and point out the GitHub repository there. If you're interested in downloading the code. There is a documented example that you can look at there, and hopefully soon we'll have the list of all of the archival mask slits uploaded there as well from our testing of those about 3,200 masks. So those would also be available. And my email is also there if you would like to discuss anything further. So